Right, ladies and gentlemen, let's continue with our course in heat and mass transfer. We are making use of the textbook of Cengel and Ghajar, and it's the 5th edition. In terms of, let's just look at the chapter or the textbook in terms of the progress that you've done so far with in this textbook. Last year in the fluid mechanics course, you obviously did chapter 1 and chapter 2. Those were introductions, and also then the heat conduction equation, and then you also did chapter 3, the steady heat conduction chapter. Then I started with chapter 4, transient heat conduction. Chapter 5 is on numerical methods, and that you do in another course. So that is why we do not do it here. And that is the CFD course that you're doing at the moment. Then chapter 6, fundamentals of convection, and chapter 7, external forced convection, and Dr. Leroux did that with you. And today I'm going to continue with chapter 8, internal forced convection, and then the chapters following that would be natural convection, boiling and condensation, heat exchangers, fundamentals of thermal radiation, radiation heat transfer, and mass transfer. We're not going to do all those chapters. Some of these chapters we will do in the follow-up course in the second semester, and some of it, and we will also make use of another textbook. So just to give you an idea. So let's continue with chapter 8, internal forced convection. Right, now what is internal forced convection? Well, I think the word tells us all. It is internal. It is things where heat transfer occurs inside things, and normally it is in geometries which are typically or can be associated with a tube or a pipe or a channel, and the typical flows are liquids and gases, and normally in those geometries heating and or cooling takes place. For us as mechanical engineers, we want to keep things internal because then we can control it, and then we can also have control over the losses. So in general, this is most probably one of the most important chapters in the textbook in terms of fundamentals. Okay, now the thing is, when we design heat exchangers or any such things, then we are normally not only interested in the heat transfer, how many kilowatts we can transfer, but what is always associated with convection heat transfer is that we need a pump or a fan that drives the process for us. And therefore, the friction factors are just as important. So in terms of what we try to achieve, there are normally two things that we try to achieve when we look at internal forced convection. The first one is to get the friction factor, because if we can get the friction factor, then we can determine the pressure drop. Okay. And then the second thing is we want to obtain the heat transfer coefficient. Okay. And it might be from a Reynolds number, which is the non-dimensionalized heat transfer coefficient, just like this friction factor is a non-dimensionalized one. Normally we want the Reynolds number so that we can get the heat transfer coefficient, and when we get the heat transfer coefficient, then we can calculate the heat transfer rate. So those are the things that we're typically very interested in. Now in terms of the chapters, how things are being put together in this textbook is we have chapter 7. Today we're going to do chapter 8. And in chapter 7, you did external forced convection. External forced convection, and in chapter 8, you're going to do internal. Now, there's one very important difference between these two modes of heat transfer. And it all has to do with the boundary layer, what happens in the boundary layer. With external forced convection, if this is the geometry, okay, then a boundary layer is going to form. And there's the free stream. And theoretically, this boundary layer can become indefinite in terms of height. It can keep on growing and growing and growing. So for example, the wind blowing over the ocean, that boundary layer will just keep on getting thicker and thicker and thicker. So that is the thing with external flow. So this boundary layer theoretically can become infinite. So that is what happens with external flow. With internal flow, we have actually the opposite, because normally with internal flow we have two boundaries in which all the heat transfer occurs. And what now happens is that the two boundary layers grow, but they always meet, or most of the times they meet. Okay? And the boundary layer cannot become infinite in size. Okay? So the boundary layer here is finite. Okay. However, the fundamentals of both of them are actually the same, and that is that the Nusselt number is a function of the Reynolds number and the Prandtl number, and also the Grashof number. I will say something about the Grashof number just now. And this one also, the Nusselt number is a function of the Reynolds number, the Prandtl number, and the Grashof number. Not different. Now the thing is, let's just look at the Reynolds number. The Reynolds number, as you know, by definition, is equal to a velocity, okay, multiplied by a characteristic length. Okay, and that is why we use L there. This might be the length of a plate, it might be the length of a car, it might be the height of a vehicle. It depends on geometry. That characteristic length that we use, divided by the viscosity. We can write it two different ways. Do it like this. Rho VL divided by viscosity, or VL divided by the kinematic viscosity. Okay, and we know it is the ratio of the inertial forces divided by the viscous forces. And what is important here is that the Reynolds number gives us an indication of when the flow will be laminar, when it will be in transition, or when the flow will be turbulent. Okay. Who of you can remember when the flow will be turbulent? At what Reynolds number? I hear some values. What do you say?
But internal tube, isn't it 2,300?
You said 2,300. Anybody else? Okay. Okay. Now I'm very thankful that you said for an internal tube. Okay. Because that is one of the most important things to remember. There is no specific Reynolds number which is being used for all geometries in terms of telling us when the flow will be laminar or turbulent. For a tube, not internal flow, but for a circular tube, then it occurs when the Reynolds number is 2,300. Over an aeroplane wing, it will be another Reynolds number. Okay, but the Reynolds number in general tells us, obviously with empirical information that we need from experiments, if the flow will be laminar in the transitional flow regime or in the turbulent flow regime. Okay. The next one is the Prandtl number. Now the Prandtl number is by definition the viscosity multiplied by Cp divided by K. And this is also known as the relative thickness of the velocity and thermal boundary layers. Let me write it out. The relative thickness of the velocity and thermal boundary layers. Okay. Now, this is a very difficult concept for students. But this year, I hope I'm going to make it very easy. So, now the thing is that typically if the Prandtl number is approximately equal to 1, okay, then the heat, the rate at which it diffuses is approximately equal to the rate of momentum diffusion. Okay, that is what the Prandtl number means in terms of its definition. Okay. Now, if it is smaller than 1, then the heat diffuses quicker. And if it is larger than 1, the heat diffuses slower. Yes, okay. Okay, now, in terms of the boundary layers, what I normally did with previous lectures, I immediately went to the boundary layers and explained this. And if you go and look at previous videos, you will see this is one of the things that has been discussed most by people. Because everybody would then say, or not everybody, people would immediately say, no, but this is wrong and this is right. It should be this, it should be that. And it is all about this thing of the Prandtl number. So this year I'm going to change my approach totally. I'm just going to stop here. And then later on, or maybe with the next lecture, I'm going to use another angle to describe to you what has actually happened here. Okay? Right, so let's just park the Prandtl number for a moment. The next one is the Grashof number. Now the Grashof number is by definition equal to G multiplied by beta multiplied by Ts minus T infinite multiplied by L to the third divided by the kinematic viscosity squared, and that gives you an indication of the buoyancy forces. Now we are not going to, in this chapter, look at the Grashof number. So in chapter 7 and 8, we have actually those two influences were neglected, just to make the work easy to understand, and then in the next chapter that will be added. Okay, so just take note, the Nusselt number actually is a function also of the Grashof number. It's not only a function of the Reynolds number and the Prandtl number. We have to add that one, but we will do that with the next chapter. Right, so in terms of terminology, if you go and read paragraph 8.1 in terms of in the introduction, you will see that the terms pipe, ducts, and conduits are used, and it is used in this chapter quite interchangeably. It doesn't really matter. A pipe is actually something that we do not get these days anymore. In the old days, pipes were casted. And that was the difference between a pipe and a tube. A tube is a soft-drawn tube or a hard-drawn tube. Those are actually known as tubes. And these days, we do not get actually pipes anymore as castings. So actually, we should talk of tubes. Okay. While a duct would be something that normally you will get in an air conditioning system, and I will get to it just now. So in terms of pipes and tubes, with pipes and tubes, normally are circular. They've got a diameter on the inner diameter. As I've said, you can call them a pipe or a tube, it doesn't matter. And their diameters can vary from very small to very large, and their roughness theoretically can be taken into consideration by this ratio of epsilon divided by the diameter. However, these days, because the pipes are hard-drawn or soft-drawn, if you go and measure the surface roughness, and you then work out the epsilon divided by d ratio, I promise you, for all practical purposes, it is equal to 0. Okay? So if you go and do it, and we've done it many times in our lab, and it works out a 0 point, and you'll have about 3 to 4, 5 zeros before something happens. So it's very, very smooth. So in general, all pipes and tubes that we work with these days and that you buy are actually very, very smooth. Now the thing is, we know obviously that they are being used to transport liquids and fluids and gases, but the thing that is very nice about them is that they can take very high pressures. Okay, they can take very, very high pressures without any significant distortions, and that is sort of, on that point, the difference between a pipe, a tube, and a duct. Ducts are typically, in terms of geometry, you'll get them like that, or something like that. Okay. And they are usually made from galvanized sheet, which is bended, and they're being used in the HVAC industry, the heating, ventilation, and air conditioning industry. And typically, ducts like this are being used in areas where there's not a lot of space. Okay, and that is the reason in many cases for these types of geometries. In the roofs, where there's not a lot of space, put in these types of geometries. So, and normally the pressure drops that they can handle is in order of about 20 kPa. And if I say pressure drop, then I mean the pressure between the inside and the outside. So normally they will have maximum pressures of about 120 kPa, and with atmospheric pressure approximately 100, the delta P pressure difference would be approximately 20 kPa. Okay. Right, so in terms of, that was just some of the important comments that were made in the introduction of the textbook. The next one is about the average velocities and temperatures. Average velocities and temperatures. Okay. Now I'm going to go back to fluid mechanics again, what you've done in fluid mechanics, because it is so similar to what happens in the heat transfer. If we look at now flow through a pipe or a tube, okay, and this is, let's call it uniform flow, and let's make this velocity equal to 0.01 meters per second. Okay. And let's suppose this tube is 150 millimeters in diameter. Okay. And this is the x-axis. So now you've done it in fluid mechanics that a boundary layer is going to develop. The fluid velocity here, which was 0.01 meters per second, the one that's going to be next to the surface because of the viscosity is going to decrease and will be 0. Okay. And because it is zero, its friend just on top of it is going to slide over it, and because it is now at a lower velocity, is going to cause a distribution in terms of the velocities. Okay, and this is the reason why this then forms. So this is called delta. Okay, and I'm specifically, if you have colors here, please use some colors. A blue and a red would do fine. For the boundary layer, the velocity boundary layer, I'm going to use blue. Okay. And that distance is equal to large R. Okay. Now, when these two boundary layers meet, if the flow is laminar, then we are going to have a velocity distribution that looks like that. Okay. Parabolic velocity distribution, and you've already derived that in fluid mechanics. And the result of that is going to be that if you would go and measure all the velocities, then it would look something like that. But there are a few things that's very important about this. The first one is, if we go and look at this maximum velocity, then this maximum velocity would be equal to 2 times the average velocity. Okay. And what is the average velocity equal to? The average velocity in this case would be equal to 0.01, and that would be 0.02 meters per second. Okay. And because of this, we know that that is sort of the average velocity there. U average. And from fluid mechanics, we can derive that the velocity profile is equal to the maximum velocity multiplied by 1 minus r squared divided by capital R squared. Okay, that equation, do you remember it? The parabolic velocity profile. So if we are interested to know at 50 millimeters from the center line, what would the velocity be at that point there? Let's call it U50. If we want to know what the velocity is going to be there, then it is very easy to calculate because the maximum velocity is equal to 0.02 multiplied by 1 minus r squared divided by 0.075 squared. Okay. And that would then be equal to 0.02 multiplied by 1 minus 0.50 millimeters squared divided by 0.075 squared, and that would give us the velocity of 0.111 meters per second. Okay. Just as a typical calculations that you've done in fluid mechanics and that I hope you are familiar with and that you understand in principle in terms of the average velocity. Okay, so there's the average velocity like that. Okay? Simple, isn't it? Okay. Now the other things that go with it is, of course, the calculation of the mass flow rate, because the mass flow rate is equal to the density multiplied by the cross-sectional area of the tube multiplied by the average velocity. Okay. And in this case, let's suppose it is water, then the density would be 1,000. The cross-sectional area would be equal to pi divided by 4 multiplied by 0.075 square multiplied by the average velocity, which is equal to 0.1, and that would give us a mass flow rate of equal to 0.1767 kilograms per second. Okay? All happy with that? Yep.
You use the radius instead of the diameter?
Oh, right, sorry. Okay, yep. Yep. Okay. Okay, and then the Reynolds number, we can calculate the Reynolds number. The Reynolds number would be equal to rho Vd divided by the viscosity. The density is 1,000, the velocity is equal to 0.1, the diameter 0.15, divided by the viscosity, 1 multiplied by 10 to the minus 3, and this, in this case, the Reynolds number is 1,500. Okay. Of course, it's less than 2,300, it's a circular tube, we know that the flow would be laminar. Okay. These are the type of calculations which you've done in fluid mechanics, you know it, and I've just done it quickly for revision because of the similarity with heat transfer. So before I continue, do you have any questions on it? Yep.
So the average velocity is 0.1 or 0.0. Mass flow rate would be?
I think it was 0.01. Do you mean here? 0.01. Okay. And here also. Okay. 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 Right. Now let's look at the heat transfer similarity. If we've got now the tube, the same tube. Okay. And here is the inlet velocity. It's equal to 0.01 meters per second. Let's suppose the inlet temperature is 20 degrees Celsius. Now temperature is not a vector, it doesn't have direction, so we cannot draw it as an arrow. So what I'm just going to do it is I'm going to draw it in terms of a length. Okay, Now, let's suppose that length would represent the inlet temperature of 20 degrees Celsius. Maybe you can draw it in length 20 millimeters or something like that. Now, this tube is going to be at a constant temperature on the outside of 100 degrees Celsius. So there it is, 100 degrees Celsius. Right, so what's going to happen now? Well, two things. The one is, firstly, we're going to have this boundary layer that's going to develop hydrodynamically, just because of the velocity distribution. But we are also going to have one that develops because of the thermal differences. Okay. How do they look like? Well, firstly, let me start by putting in the hydrodynamic one first. But I'm going to draw it shorter, okay, just to create some more length for me. Okay, so this is the boundary layer that developed hydrodynamically. So there's the boundary layer thickness at any specific point x downstream. And the velocity distribution is going to look like this parabolic one, like that. And in that, we've got the velocity, the maximum velocity, and we've got the velocity as a function of r. Now, the temperature one is also going to now develop, because now we've got fluid at 20 degrees, which is being heated with a wall which is at 100 degrees. Okay. So what is now going to develop is the thermal boundary layer. The thermal boundary layer is going to develop like that. Okay. Now in this case, I'm just showing it just as an example of the thermal boundary layer being fully developed after the velocity one. But it can be at the same time or it can be before, and I'm going to get to that just now. Okay. So now in terms of the thermal boundary layer, how does that look like? Well, if you want to show that temperature as 100, then maybe you can put a line there of 100 millimeters on the wall. And then here on this side also. While here on the inside, we will have something like that. That would be 20 millimeters. Okay. The fluid on the inside, on the center line, would not even know what is happening on the boundary layer, okay, on the surface. So those two is going to meet like that. You're going to have a temperature distribution looking something like that. So 100 on the outside, decreasing to maybe a value of 20 on the center line. Okay. Right, so this is the complication that we have in internal forced convection, specifically if the flow is laminar. If the flow is laminar. Now, why is this a complication? It's a complication because if we want to do heat transfer calculations, we want to say, well, the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface temperature minus something. Now, the question is, what is the something? The something, in this case, can be many different values. So just like what we've done with the velocity boundary layer, calculating the average, we can calculate the average for the temperature. Do you agree? Do you agree? No, it's not right. Halfway right. Because the thing is, and we will do it just now, is that this velocity here is very low. Okay. So we have to also take into consideration when we do this the mass flow rate. So the mass flow rate will have an influence on the calculation of an average temperature here, Tm. So that is our temperature Tm. Okay. And that is important to us because we want to say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface temperature minus Tm. Okay. And we need to get Tm. So the principle how we get Tm is actually very easy. If I can make this sketch a little bit larger, like that, and have some, let's call it control volumes, like that. And then look at this temperature profile like that, knowing there it is equal to 100 there. And let's suppose it is 90 there, and here it is equal to 85. Okay. And let's call that A, B, and C. And we can have a diameter here on the outside. We can have a D1 and a D2. So for all of them. So what we need to do is we need to say that the mean temperature is equal to the temperature here, which is in A, multiplied by the mass flow rate of this part. Okay? Right. Plus the temperature here, let's call that a B, multiplied by the mass flow rate of B, where B is now this pink section there, that annulus there. You see? Plus, obviously, all of them, and then we have to divide by the total mass flow rate. Okay. Then we will get the right mean temperature. Do you agree? So we have to take into consideration, we cannot just look at the temperature profile, we also have to use the mass flow rate, which drives the temperature profile. Okay. And the result of that is an equation in your textbook looking like this. The mean temperature is equal to 2 times divided by the average velocity multiplied by r squared multiplied by the integral from 0 to r, the temperature as a function of r, the velocity as a function of r dr. And that is equation 8.4 in your textbook. Okay. It is not well derived in the textbook, but this is the principle. If you understand this principle, then it's exactly what he did. Okay, so it made use of the fact that it said that the energy or the heat transfer to the fluid is equal to the mass flow rate, the Cp multiplied by a temperature. See the mass flow rate and the temperature of each section in the cross section. Okay? So, now let's suppose, just as an example, if you have a velocity profile which is equal to 0.02 multiplied by 1 minus r squared divided by capital R squared, like that, and you've got a temperature profile which is equal to minus 80 multiplied by minus a quarter minus r squared divided by r squared. Okay. And let's suppose the radius of the tube is 75 millimeters. If you make use of those two profiles, the velocity profile and the temperature profile, you do the integration using this equation 8.4 in your textbook, then you're going to get that the mean temperature is equal to 46.7 degrees Celsius. Okay. Right, now you've done it with forced convection. That distance is, of course, the thermal boundary layer. Okay. Okay. Now, this is very important for laminar flow. For laminar flow. In turbulent flow, it is not necessary to do it. Why? Because in turbulent flow, The velocity profile looks like that. Okay. It's plug flow. And because it's plug flow, the temperature profile will also be a plug flow type of temperature profile. So we only need to do these calculations for when we have heat transfer cases in internal forced convection if the flow is laminar. It's not necessary for turbulent. I beg your pardon? What is?
Plug flow.
Oh, what is plug flow? Sorry, you don't know what plug flow is. Plug flow is the velocity profile is like a plug. Like this. What did you call it? Plug. Plug flow. In literature, you'll see called plug flow. Okay. Plug flow. Okay. So it's like a plug. Okay. There's no profile in terms of velocity or temperature. Okay. Any other questions? Okay. Now, let's look at the characteristics that we have between laminar flow and turbulent flow. I mean, you know this stuff, but I'm just going to go through it very quickly. If the flow is laminar, okay, and you would take measurements of the velocity as a function of temperature, and you've got very good instrumentation, then the velocity will be without any fluctuations. Okay. In this region, if you do it here, the velocity, the average velocity will be constant. So U average is a constant. However, if you go and take very, very fine measurements, you will see that there are lots of fluctuations of the velocity profile. So this is laminar flow, this is turbulent flow. Okay. And you were correct, if the Reynolds number is typically less than 2,300, then the flow would be laminar. When will it be turbulent? Well, it is not so easy to say, but normally it is definitely turbulent at the Reynolds numbers larger than 10,000. Okay? But it can be turbulent down to Reynolds numbers of 4,000, maybe 3,000. And then in between we've got the transitional flow regime. Okay? So, why is this important? Well, it is important if we now look at the Nusselt number. The Nusselt number, which is a function of Reynolds number. If the flow is laminar, then typically the Reynolds number would be something like that. I sort of don't know how to draw it here. So you can draw it as a horizontal line if it is what we call totally forced convection. In most cases it is higher, it will do something like that up to the point when you get transition, and then you will have it increasing like that. So this is typically laminar flow and that is turbulent flow. Okay. These cases we will get to it a little bit later. In industry, mostly you work in a turbulent flow regime. There are not many applications where you work in the laminar flow regime, but it is something that sometimes happens, and it usually happens. When will it usually happen if we look at the Reynolds number? When will it normally start becoming very important? It will start becoming important if the diameters starts becoming very small, so in microchannels, typically being used in the cooling of electronic applications. So if you make this smaller and smaller, you'll see the Reynolds number becomes smaller and smaller. So that is the first case, and the other case is when the viscosities starts becoming very high. So fluids with high viscosities, oils, glycols in chiller is a very good another application. In those cases, then the Reynolds number can become into the transitional flow regime, or close to the transitional flow regime, or into the laminar flow regime. Now, in terms of the Reynolds number, you all know the Reynolds number as equal to rho v d divided by the viscosity. However, when you start doing lots of calculations, you will see that in many cases there is an easier way of writing down the Reynolds number, which is very convenient. So if we look at the circular tube, which will be the cases that we will normally look at, and that is the velocity, then the mass flow rate is also equal to rho A multiplied by V. Okay. So from this, we can write that rho multiplied by V is equal to the mass flow rate divided by the area. And that is also called the mass flux. The mass flux. Okay. Now, that term, rho multiplied by V, is equal to that term there. Okay? So if you do the substitution in there, then it is equal to the mass flow rate multiplied by D divided by A and the viscosity. Okay? And the area A is the cross-sectional area. It is equal to pi divided by 4 multiplied by D squared. So the result is, if you go and do the substitution, then the Reynolds number can be written as 4 times the mass flow rate divided by the viscosity, pi, and the diameter. So why is this so convenient? Because in most cases where you've got heat exchangers, the mass flow rate will be given. So normally, what we do is we will not normally take the mass flow rate and then go and calculate the velocity and then come back and calculate the Reynolds number. We will normally immediately just use the mass flow rate, the calculation of the Reynolds number. Just save some time. Okay. Okay, now, if we get to tubes which are non-circular, if we go back to the beginning of the lecture in terms of the types of geometries that can be considered, these are typically geometries that occurs in internal forced convection. And you'll see that a lot of the literature, a lot of work has been done, but most of them are for circular tubes. And work hasn't been done for every possible configuration. It's too much experimental work. Now, fortunately, people have found that in terms of the Nusselt number and the friction factor that we are interested in, if we based it on the hydraulic diameter, then many of the equations are still valid. Okay? So it therefore means that if we go and calculate the Reynolds number of a non-circular tube and we based it on the hydraulic diameter, so we normally it would be rho V multiplied by the diameter, and if you look at any of those cross-sectional areas, then you don't see a diameter. If you base it on the hydraulic diameter, then it works. So calculate the Reynolds number based on the hydraulic diameter, the Nusselt number based on the hydraulic diameter, and then you can do all the calculations. And then the same for the friction factor, of course, and that you've done in fluid mechanics. So the pressure drop would be equal to the friction factor multiplied by L, not divided by the diameter, but the hydraulic diameter, multiplied by rho V squared divided by 2. And then you can get the pressure drop. So for those of you who cannot remember the definition of the hydraulic diameter, the definition is equal to 4 times the flow cross-sectional area divided by the wetted perimeter. Okay, so OC is the flow cross-sectional area, and P is the wetted perimeter. So let's look at the case of a square duct. Square duct, typically like that. That is equal to A multiplied by A. Okay. Then the hydraulic diameter would be equal to 4 times. Okay, now the flow, let me put it in like that, would occur through there. Okay. So it is 4 times the cross-sectional area of the flow. What is the cross-sectional area of the flow? It is A multiplied by A. Okay. And the wetted perimeter, the flow wets this surface here, that one, and that one. So it is 4 times A. Okay. So the result is that the hydraulic diameter is equal to A. Okay. Let's do it for a rectangular duct, like that. A and B. The hydraulic diameter is 4 times, that's the flow through there, 4 times the cross-sectional area. The cross-sectional area is A multiplied by B. Okay. What does it wet? It wets that leg there, that one plus B plus A plus B. Yeah. Okay? Now look at this one. That is A. That is H, and that is equal to B. Write down the hydraulic diameter for me now. What is the hydraulic diameter for that case? So there's the fluid. Okay. It is 4 times the cross-sectional area of the flow. Okay. And that would be equal to H multiplied by B. Okay. The cross-sectional area of the flow. Now divided by the wetted surface. And the wetted surface is equal to H plus B plus H. You agree? Okay. And you will have to think of it in terms of the friction factor, for example. If you go and take off this lid, it would have no influence on the pressure drop. And that's the reason why you calculate the hydraulic diameter like that. Okay. Let's look at another one that we're going to use quite a lot. And that is flow through an annulus. That is D inside. And let's call that one D outside. Okay. That is the solid tube, like that. Solid tube, like that. Okay. This is also solid. And let me get the color here. Let me use the yellow. So the yellow is the flow. Okay. Through which the flow occurs. Okay, so D outside is the inner diameter of the outer tube. Do you see it? Okay. And DI would now be the outer diameter of the inner tube. Okay. So the hydraulic diameter in this case is 4 times the cross-sectional area of the flow. What is the cross-sectional area of the flow? It is pi divided by 4 d outside minus d inside square. Okay? Do you agree? Divided by the wetted perimeter. Okay. Now the wetted perimeter would be this one here, pi d outside plus the inside one. Okay. This perimeter is wet here, and that perimeter is wet. This one is pi multiplied by that diameter. That one is pi multiplied by that diameter. Okay. So the force disappear, the pi disappear, and the result is, as you can see, you can write that as dO plus di, dO minus di, divided by dO plus di, and the result is d outside minus d inside. Okay? We'll continue with the next lecture. Thank you very much.